that these two spaces are never equal. There is always one which is bigger than the other one. As soon as S is of course a singular value of one of them. Okay? And moreover, so either we have equality U of S, or U of S intersection U of photonaut is S U of S, or S U of S intersection U of photonaut equals E U of S. Okay? So in that case, I will say that S is H dominant because the eigenspace associated to S has the biggest dimension when it's associated to H squared. Then I will say that S is K dominant because the eigenspace, the biggest eigenspace is S U of S, which is associated to K squared. Okay? So of course it may happen that one of them, and this is the generic case, one of them is 0 and the other one is that of dimension 1, the case of singular values. But in general you have this. And it's very important to have all that kind of multiplicity in order to handle all kind of data. Okay? So now there is some additional property about these singular values, and this additional property is a very nice exercise based on the formula KU square equals HU square minus dot UU, which tells you that these two operators are rank 1 perturbation of each other. Okay. So it's better because it's less wet, but it's not so good because it does not erase at all. But okay. So if you use the classical min-max principle for estimating the eigenvalues of a non-negative compact operator, then you get immediately that if I order the singular values associated to U like this, then alternatively this one is H dominant, the second one is K dominant, the third one is H dominant, etc. That is the point. Okay? And of course this sequence may be either infinite or finite. The case of a finite sequence means that HU and of course KU at the same time is finite rank operator. Well, this is a very old result. We know exactly what kind of U are such that HU is finite rank. It was proved in 1881 by Leopold Kronecker. And he proved that this corresponds to the fact that U of Z is a rational function. And of course the rank is related to the degree of this rational function, with of course no pole under closed unit disk in order to preserve the property of half space. So we know, and in fact it's rather easy to check it by hand. If you start from a rational function with a given degree, and you put it in the equation, you see that you get the rational function for all time with the same degree, and you can even write the ODE system, which is rather complicated, on the coefficients. Okay? I know that this system is integrable in the Euclid sense, okay? Which is in fact a consequence of what we are going to do. So, now I told you, I want to define a nonlinear Fourier transform. Here, as the first part, this is my sequence here. Oh, I forgot to tell you that there is of course another condition if I assume that the sequence is infinite. In the case of an infinite sequence, since U is in H half, this means that the trace of HU square is finite. So U is in H half tells you that the sum of the multiplicities times SK squared is finite. So NK is a dominant multiplicity. So the biggest one, whatever, I mean the other one is just NK minus 1, so it's equivalent for the... So I prefer to write it that way, because NK is at least 1. Okay. Now I'm going to find the sum. For the second part, I'm going to use some results which started in the 70s, the early 70s, with the school around Trine. And in particular, a beautiful paper by Adamian, Arov, and Trine, which was published in the Russian math surveys, and which tells you something about the action of HU on these spaces, of HU for instance on AU of S. So assume for instance I have a dominant, H dominant eigenvalue. Okay? And singular value, so you should write it singular value. Now, of course, I can define then US. US is a orthogonal projection of U onto the space, the space AU of S. I know that this guy is not zero, precisely because this is dominant. Because AU of S, which is the intersection with AU of S, with AU of S. Okay? So now I look at this space, and this is a vector VF, which is HU of US divided by S. So this is also AU of S, because HU and HU square are commuting. Okay? Now we'd like to see a connection between VS and US. So Adamian Arov Trine call this pair US DS the Schmidt pair, or maybe some other people before that. The Schmidt pair for this operator, and when you have a singular value of an operator, is just given by this. HU of US is SVS, and HU, or sometimes HU started here as the same, of VS equals SUS. This is a Schmidt pair. Okay, so it's another way to say that S is a singular value. Now, I claim that these two functions are functions of C, which are holomorphic functions. So I can look at the quotient of these two holomorphic functions on the unit disk. This quotient has very nice properties. And in fact, well, just to imagine the multiplicity is just 1. In that case, these two guys are collinear, so this quotient is a constant of modulus 1. So it's an angle. But in general, Adamian, Aroff, and Tran proved that it's a function of modulus 1 on the circle, and more precisely, it's of that kind, T of G divided by G n minus 1 T bar 1 over G, where T is a polynomial of degree at most n minus 1. It's a kind of remarkable finiteness result related to these Schmidt pairs. Okay, I claim that, this is general. I mean, this is true for any Schmidt pair. So any pair of vectors satisfies this. Now, in our case, we can specify this because US is not any kind of part of Schmidt pair. And the lemma is that we prove with something Rayleigh, is that in fact this quotient, of course this is a meromorphic function, but this meromorphic function